Alright, hello everybody. We are going to work through a 3D equilibrium problem using the right hand rule instead of using R cross F to find the moments. Okay, we're going to use this 3D problem right here. And of all the 100 or so videos giving examples like this on YouTube, and even the solution manuals in the book, they would work this problem using vectors with the R cross F method to find the moments. However, in our class we were taught that you were only to use R cross F if you were dealing with a skewed line that is not parallel to any of the axis. For most of these problems, however, we are able to use the right hand rule and find the moment by using the force times the perpendicular distance, just like you would in 2D problem. This method gets you the same answer, but it will be much faster, especially because most of the time you're going to be taking this as a timed exam, especially in the FE exam. So let's start real quick taking a look at a regular 2D problem with a beam, something nice and simple, which we already know how to do. And so to solve this one, we would find the moment about A, and we know that's equal to 0. We have this negative 200 newtons, so if we hold still at the point A, we take our right hand and we curl our fingers in the direction that the rotation would create. So if we're looking at this 200 Newton force, it's pushing down as if it were causing rotation in this direction. So take your hand, curl it this way. The thumb is pointing into the page, even though I can't quite turn my hand like that. Thumb points into the page. That is a negative moment, so our formula is going to give a negative sign, negative 200 times the perpendicular distance of 1.3 meters. And then we have the force at B. The reaction force pointing up this way would create a rotation in this direction, so we wrap our fingers this way. Thumb points up out of the page. That's the positive Z direction. So positive B times a perpendicular distance of 1.5 meters minus this 250 Newton force, which is again going this way. It's a negative 250 times 2 meters, and we know this equals 0. And you can come through and work this to see that B ends up being 506.67 newtons. And then from there you can take the sum of the forces in the y direction and find out what the reaction at A is as well. Okay, those are easy. Now, normally when you would take on a problem like this, they begin wanting to make position vectors, and then you have to do a cross product of this position vector times this force, all which is rather tedious and takes a long time. So normally in 2D we have the moment of a point equals a force times a perpendicular distance. And then in 3D, the moment of a point is the position vector cross the force vector. And then in order to get the moment about a line, which is a scalar, take this moment about the point, which we found here, and dot it with the unit vector, which represents the line you wish to take, which would be the same thing as taking your R cross F and dotting it with the unit vector. Okay, again, that would take a long time. Okay, in 3D, we take the moment about a line by mentally grabbing a hold of the line with the right hand, and pointing our fingertips in the direction of the rotation. And the thumb will point along that axis in the direction which will give us the sign, either positive or negative, of that moment. And we then use the sign along with the force times the perpendicular distance, just as if we were doing a problem with 2D. Alright, so what we're going to use here is this formula. The moment is a force times a perpendicular distance. Also keep in mind, if a force is parallel to the line, it creates no moment about that line. Likewise, if a force intersects the line which we are taking the moment about, then it creates no moment about that line. Okay, and the first thing we want to do, of course, is to draw our free body diagram. Okay, so here we have our free body diagram. And I'm going to go ahead and add the slope triangles real quick to these cables. This one right here, or this distance from B to A, was 480 millimeters for our drawing here. 480 millimeters. It's a good idea to go ahead and change everything into meters. So the distance of this will be 0.48 meters. Okay, the formula for force times the perpendicular distance in newtons is always with the distance in meters. It's a good idea to go ahead and change everything to meters, just in case. Alright, our distance in the z direction here is 0.2. Alright, and so the magnitude of the hypotenuse here, of course, is given by the square root of this squared plus this squared, is going to be 0.52 meters this way. And for this cable over here, DG, make our little triangle on this one, and this distance from here to here is 0.14 meters, and from here to here it's going to be 0.48 meters, and the magnitude on this one is going to be 0.5 meters. Okay, so what we want to do here is we want to take the moment about an axis, and generally you pick one that will eliminate unknown quantities so that you can find certain quantities. If we take the moment about the x-axis, this cable BE, the force of that intersects x and therefore will not create a moment. These reaction forces at A are intersecting the x-axis and will not create a moment. This force of cable CF is parallel to x and will not create a moment. So I have this force of 350 newtons represents the weight of the frame. That will create a moment about the x-axis, and this cable DG will create a moment as well. So if I look at this 350 newton force, you see that if this x-axis were to be stationary, the 350 newton force here would cause rotation in this direction. It comes down. So the rotation does not go this way, it goes this way. Grab a hold of the axis, rotation goes this way. My thumb is pointing now in the negative x direction. So we sum the moment about the x-axis. This 350 newtons right here will give us a negative 350 times this perpendicular distance. If you remember from the original picture here, 350. This is a 150 millimeter distance here. Convert everything into meters, that is 0.15 meters. Now, cable DG. The x component, if we're breaking this into components, the x component is parallel to the x-axis over here, and therefore will not create a moment. Our moment is created by the y component of cable DG, as if it were going straight up from here. We have a y component and this z distance to the x-axis. Now this one is coming straight up here, and so the rotation it would create would be this direction. So we take our hand, curl the fingers like this, thumb is pointing in the positive x-axis. So I call this a positive, whatever the force of DG is. Now I want only the y component of this force, which will be the sine, which is opposite over the hypotenuse, which means if this is our angle here, the opposite is 0.14, the hypotenuse is 0.5. So we're going to multiply this force by 0.14 over 0.5. This is the force times this perpendicular distance, which was 300 millimeters or 0.3 meters. Alright, and so all of this will equal 0 as the beam is in equilibrium. So notice what's happening here. We're taking the moment about the x-axis. Here I have a y force and a z distance. Here I have a y force and again a z distance. And every time you do this, it should be like that. You're taking the moment about x, you'll have a y force and a z distance, or maybe even a z force and a y distance, right? But all three components should be taken care of like this. Okay, so if we take care of this real quick, you can go through and find this unknown. So now we know that the tension of cable DG is 625 newtons. Alright, next what we will do is sum the moments about the z-axis here. Notice first that the reaction forces at A intersect z and will not create a moment. is this tension from cable BE will intersect Z and not create a moment. Alright, so if we sum the moments about the Z-axis equal to 0, first we have the force of CF. Now if you grab a hold of the axis, you can see the force from CF is pulling back this way. This would create rotation in this direction. So you grab a hold of the Z-axis as if it's in your hand. The rotation goes with my fingers like this, and my thumb is now pointing in the positive Z direction. That's going to be positive force of CF times this perpendicular distance. Which this distance from C to B is 140 millimeters, which is 0.14 meters. Then we have the weight of 350 newtons right here. Now about Z, this would create a rotation in this direction. So we grab a hold with the fingers in rotation like this, and our thumb is pointing in the negative Z direction. This is negative 350 times the perpendicular distance from here to the axis, which is 0.48 meters. Now with the cable DG, the X component of this cable would intersect and therefore does not create a moment. It's only the vertical component which creates a moment. And this component creates a positive moment, would rotate it this direction, thumbs in the positive Z direction. So this is going to be plus the tension of DG, and we only want the vertical component, and so this is going to be the sine, that is the opposite over the hypotenuse. And so it'll be force DG times 0.14 over 0.5. And then we have the perpendicular distance from here to here, again, as 0.48. And this is equal to 0. Now we know from before that tension DG is indeed 625 newtons. So we should be able to go through and solve this to find tension in CF is 600 newtons. Again, notice when we're setting this up, we're taking the moment about a Z-axis. Here I have an X force times a Y distance. Here I have a Y force times an X distance. Here this whole thing represents a Y force and an X distance. Alright, next we are going to sum the moments about the Y-axis. We're going to see what would cause rotation around the Y-axis here. Notice that cable CF would intersect the Y-axis, will not create a moment. And the 350 Newton force of the weight is parallel to Y and will not create a moment. Likewise, the X component of cable BE intersects and will not create a moment. And the Y component of DG is parallel and will not create a moment. So now we say that the sum of the moments about Y equals 0. So from BE here, And you see that if this cable BE were pulling this around, it would create a rotation in this direction. If I curl my fingers in that direction, it rotates that way. My thumb is pointing down in the negative Y direction. So this will be negative BE, and we are only interested in the component going this direction. If this is the angle, this is going to be the sine, the opposite over the hypotenuse, which is 0.2 over 0.52 times this perpendicular distance from here to here, from A to B, is 0.48 meters. Then we have cable DG. The x component of this force would cause the y-axis to rotate in this direction. So we curl our fingers, we grab hold of that y-axis, curl our fingers in this direction. Our thumb is pointing up in the positive y direction. So this is positive dg. And this time we are going to need the x component of this force. Okay? So this is the cosine, or cosine, which is the adjacent over the hypotenuse, which is 0.48 over 0.5 times this perpendicular distance, which is 0.3 meters. So again, we're taking a moment about y, the y-axis. Here I have a z force, and this is our x distance. Here I have an x force, and this is a z distance. And again, we already know that dg is 625 newtons, so we should be able to go through and solve this. Say that BE is equal to 975 newtons. So far, we have determined the tension cable BE is 975 newtons, and the tension in cable CF is 600 newtons, and the tension in DG is 625 newtons. Next, we need to find the reaction forces from AY, AX, and AZ. And we can do this just by summing the forces in the X, Y, and Z directions. But real quick, I want to show you one other thing. One of the other little tricks that you use with other problems, although we don't necessarily need it in this case, is we can take the sum of the moments about any arbitrary line, and we can even create a new axis. Say we take this line over here and we extend this, and we will call this the Z prime axis. Alright, notice that when we cut through here, I eliminate some other unknown quantities. So likewise, we could take the sum of the moments about Z prime Now, when we talk about Z prime, we have the Y component of the A reaction force creating a moment in this direction, which is the negative Z prime direction, So that's going to be negative AY times this perpendicular distance of 0.48 meters plus this cable CF is creating a moment this way. So it's going to be plus CF times this perpendicular distance, which is 0.14 meters. And from this you could determine that the Y component of that reaction force there is 175 newtons. Although in this situation we don't really need to use that. Instead, we can simply sum the forces here in the x direction. So we have AX pointing in the positive direction, call that positive AX. And then we have the force CF going in a negative x direction, CF. Then we have the x component of BE in the negative direction, negative BE times the slope, which is going to be the cosine. So it's 0.48.52. And then we have the DG component. X component here is going in the negative direction. DG times the cosine, which is 0.48 over 0.5. Since we already know what CF, BE, and DG are, you should be able to solve this to find that AX is equal to 2100 newtons. Now if we sum the forces in the y direction, you have the y component AY. It's a positive AY. And we have this DG, the y component of DG, is plus DG times the sine is 0.14 over 0.5 equal to 0. So AY is equal to 175, which we already found a moment ago. Which is why I said it wasn't necessarily needed to sum the moments about Z prime. The last part here, we sum the forces in the Z direction. And you have AZ. And the Z component of cable BE will be positive BE times the sine, which is 0.2 or 0.52 equal to 0. And from that you can see that AZ equals a negative 375 newtons. So our reaction force at A is equal to 2100 newtons in the x direction and 175 newtons in the j direction and a negative 375 newtons in the k direction. the tension from BE was 975. The tension in CF, 600 newtons. And the tension in DG was 625 newtons. Now, this should take us less time than it would if we did the whole problem with R cross F. Hopefully, with some practice, you guys will get good at this and be able to do it quickly. All right, have fun.